Look up at the night sky. Every star you see, every galaxy spinning in the cosmic void, every particle of matter that exists, all of it is marching toward an end. But here is what keeps physicists awake at night. Nobody actually knows how that end will come. This is not a gap in our knowledge that can be filled with a few more experiments. This is a mystery that touches the deepest laws of reality itself. We stand at a moment in cosmic history where we can see the universe changing before our eyes, accelerating towards something we cannot fully predict. And the strangest part? The force deciding our fate is something we cannot see, cannot touch, and barely understand. For decades, scientists believed they had the universe figured out. Gravity was the dominant force. Everything that goes up must come down, right? Throw a ball into the air, and Earth's gravity pulls it back. Launch a galaxy into space, and the collective gravity of all matter should eventually slow its motion. The universe exploded outward in the Big Bang, and gravity has been working ever since to rein it in. Eventually, we thought, that expansion would slow down, stop, or even reverse. Then came 1998. A team of astronomers pointed their telescopes at distant supernovae, exploding stars so bright they can be seen across billions of light years. These cosmic lighthouses allowed scientists to measure how fast the universe was expanding at different points in history. They expected to find the expansion slowing down. Instead, they discovered something that shattered every assumption. The universe is not slowing down, it is speeding up. Without any additional force pushing it, without any visible source of energy, the expansion itself is accelerating. Space is stretching faster and faster on its own, and gravity alone cannot explain it. This discovery earned the researchers a Nobel Prize, but it also opened a door to profound uncertainty. What they found was not an answer. It was a deeper question. At small scales, gravity works exactly as expected. It holds you to the Earth, keeps the moon orbiting our planet, binds stars into galaxies. But at the largest scales, across billions of light years, the universe behaves differently. Something is overpowering gravity. Something is pushing space itself apart, and that push is getting stronger with every passing moment. We call this mysterious force dark energy, and it makes up roughly 68% of everything that exists. Yet we have no idea what it truly is. It could be energy embedded in the fabric of space itself, appearing from nothing and pushing outward. It could be an entirely new field, something beyond our current physics. What we do know is this: how dark energy behaves over time will determine whether the universe ends in ice, fire, or something far stranger. This is not a question with one answer. Several endings are possible. The universe could expand forever, growing colder and darker until even atoms decay into nothingness. It could tear itself apart in a violent cascade of destruction, ripping galaxies, stars, planets, and even the fabric of space-time itself. It could collapse back into a singularity, crushing everything into a single point, or it could rewrite the laws of physics in an instant, erasing everything we know in a wave of cosmic annihilation. Each scenario depends on the nature of dark energy and how it evolves over trillions of years. The universe's fate is tied to the deepest laws of physics, laws we are still struggling to understand. And as we stand here, on a small planet orbiting an average star in an unremarkable galaxy, we are trying to answer the ultimate question: how does everything end? Dark energy is the hidden engine behind everything that will happen to the universe, including every ending that will unfold in the later parts of this story. It is not a side character, it is the invisible ruler of the cosmos. Right now, the best measurements in cosmology tell us that dark energy makes up about 68% of the total energy content of the universe. Ordinary matter, everything from stars to planets to your own body, is only a tiny fraction in comparison. Yet despite its dominance, we do not know what dark energy is made of. It is not ordinary matter, not dark matter, and not radiation. It does not emit light, does not absorb it, and does not seem to interact with particles in any familiar way. What dark energy does is even stranger than what it is. It causes space itself to expand faster over time. This is not just galaxies moving through space. The fabric of space is stretching, and as it stretches, the rate of that stretching increases. The effect is tiny on human scales, but across billions of light years, it reshapes the entire universe. Dark energy acts everywhere, even in regions that look completely empty, and its influence grows as the universe grows. To explain this, physicists say that dark energy has negative pressure. In normal situations, pressure resists compression but does not make space expand. Dark energy is different. Its negative pressure pushes space apart. This property is what drives the accelerated expansion, overpowering the attractive pull of gravity on the larger scales. Without this negative pressure, the universe would slow its expansion, and its fate would be completely different. There are leading ideas about what dark energy could be. One is vacuum energy, a constant energy of empty space predicted by quantum field theory. Another is a new dynamic field that changes slowly over time, which could lead to very different futures. A gentle big freeze, a catastrophic big rip, or even a future collapse. Each possible behavior of dark energy corresponds to a different cosmic ending, which you will see in the coming parts. The existence of dark energy was discovered through observations of distant Type Ia supernovae in the late 1990s. These stellar explosions have nearly uniform brightness, allowing astronomers to use them as standard candles to measure cosmic distances. When researchers compared how bright these supernovae appeared with how fast their host galaxies were receding, they found that the expansion of the universe was accelerating, not slowing down. That single realization forced a rewrite of our picture of the cosmos. Without dark energy, gravity would gradually slow the expansion from the Big Bang, and the universe might eventually recollapse or coast forever at a steady rate. With dark energy, everything changes. It decides whether galaxies drift away into eternal darkness, whether space tears itself apart, or whether some deeper instability rewrites the laws of physics themselves. The fate of everything you know depends on this invisible component, and to understand the possible endings, we must now follow each path. Dark energy opens in front of us. Dark energy has taken control of the story. It dominates the universe and quietly dictates what can and cannot happen next. If it keeps behaving the way it seems to today, then the future of the cosmos is not explosive or sudden. It is something far more unsettling. It is the big freeze, a slow and quiet death, where everything fades, not with a bang, but with an endless whisper. In this scenario, dark energy stays roughly constant in strength over time. It does not suddenly increase to tear the universe apart, and it does not fade away to let gravity pull everything back together. Instead, it continues calmly pushing space to expand faster and faster. As space stretches, galaxies drift farther and farther apart, until the light from distant galaxies grows so red and faint that no observer can ever see them again. One by one, entire galaxies will slip beyond the cosmic horizon, disappearing not because they are destroyed, but because their light can no longer reach anyone. Inside each remaining island galaxy, the story also begins to slow. Stars are born from cold clouds of gas, but that gas is a limited resource. Over billions of years, stars use it up. New stars form more slowly, then rarely, and eventually not at all. The bright, blue young stars vanish first, leaving only long-lived, dim red stars to carry on the last light of the cosmos. Given enough time, even those final red embers burn out. The night sky, once filled with brilliant points of light, becomes emptier and emptier until no new stars shine anywhere. What remains then are the leftovers of a once active universe. White dwarfs cool into black dwarfs, cold cinders of dead stars. Neutron stars and black holes quietly orbit in the dark. Matter itself is still there, but it is spread thinly across ever-expanding space. The average distance between any two objects grows so large that interactions become incredibly rare. Galaxies no longer collide. New stars no longer ignite. There are no energy-rich environments left to power complex processes. Even black holes, which seem like the ultimate survivors, do not last forever in this picture. Over unimaginably long times, black holes slowly evaporate through what is called Hawking radiation, leaking tiny amounts of energy back into space. The most massive black holes in the centers of galaxies would take an almost inconceivably long time to disappear, but eventually they too would vanish, leaving behind only a thin sea of low-energy particles. In the distant future of a big freeze universe, there are no meaningful energy differences left. Entropy, the measure of disorder, creeps steadily toward its maximum. Without temperature differences, nothing can flow. Without flows of energy, no work can be done. No stars can shine, no chemistry can proceed, no life can survive. There is still space, still time, still the ghostly presence of particles, but there is nothing left that can change in any interesting way. The universe becomes cold, dark, and silent. Motion slows towards stillness. Every structure that once existed is either gone or frozen in a state that might as well be permanent. This is the quiet cosmic graveyard that awaits if dark energy stays as it is. Yet this is only one path. If dark energy behaves differently, the ending might be far more violent than this slow fading into night. In the big freeze, the universe fades into darkness. In the heat death, it goes one step further. The universe does not just grow cold and empty. It becomes a place where, in a deep physical sense, nothing meaningful can ever happen again. To understand why, start with a simple rule from thermodynamics. Entropy always increases. Entropy is often described as disorder, but more precisely it measures how spread out energy is. At the beginning, shortly after the Big Bang, the universe was hot, dense, and full of usable energy. Over time, that energy has been spreading out, flowing from hot places to cold ones, powering stars, planets, and life along the way. Every star that shines and every process that runs is part of this one-way journey toward higher entropy. In a big freeze universe ruled by dark energy, expansion keeps stretching space and separating galaxies. Stars stop forming, black holes evaporate, and matter becomes thinly spread. Heat death is what that future looks like when entropy has finally done all it can do. Energy becomes evenly distributed everywhere. There are no hot regions and no cold ones, no gradients to drive motion or reactions. The universe reaches thermal equilibrium, a uniform state where nothing can naturally change. Imagine a box of gas. At first, you can have a hot side and a cold side, and heat flows from one to the other. Eventually, if you wait long enough, the temperature equalizes. At that point, nothing else happens on its own. The system is not dead in the sense of disappearing. It is dead in the sense that it is done evolving. Now stretch that idea to the entire universe. That is heat death. In this distant future, there are no stars, no planets, and no complex chemistry. Even atoms themselves may not be stable forever. Many theories predict that protons will eventually decay into lighter particles over incredibly long timescales. If that happens, then the very building blocks of matter slowly vanish, leaving only a thin bath of radiation and elementary particles drifting through ever-expanding space. Black holes, once the final sinks of structure, also disappear in this picture. Through Hawking radiation, they emit particles and lose mass until they evaporate completely. The largest black holes formed from the hearts of galaxies take an almost unimaginable amount of time to fade. But given enough time, they too are gone. What remains after their evaporation is just more low-energy particles, spread even more thinly. Time in such a universe still exists, but it loses its meaning. Normally, time is marked by change. Stars forming and dying, galaxies colliding, planets cooling, life evolving. In heat death, almost nothing happens. The universe has reached the maximum entropy allowed by its contents. There are no large-scale structures left to rearrange, no significant reactions left to occur, and no free energy that can be tapped to perform work. This vision of heat death is not violent. There is no final explosion, no sudden collapse. It is a slow, relentless slide towards stillness. Many cosmologists consider some version of this scenario the most likely outcome, especially if dark energy remains similar to the cosmological constant. The Big Freeze describes the fading of structure. Heat death describes the final state when that fading is complete. Yet even here, the story is not entirely closed. Our understanding of entropy, quantum mechanics, and gravity is still incomplete. The deepest laws of physics that drive this cosmic cooling may also allow for fluctuations, cycles, or new beginnings that we do not yet understand. And if dark energy changes in the far future, the universe could escape this quiet end and head towards something far more dramatic, as the next possibilities will explore. So far, the endings we have explored are slow and almost gentle. The universe cools, empties, and drifts towards stillness. But there is a far more unsettling possibility hidden in our current theories of physics, one that does not wait for trillions of years of gradual change. It suggests that the entire universe, including the laws that define it, might not be truly stable at all. According to quantum field theory, every field in nature has energy levels just like electrons in an atom. The lowest possible energy state is called the true vacuum, but a system can sometimes get stuck in a higher energy state that is stable enough to last for a very long time, even though it is not the absolute lowest. This is called a false vacuum. It is like a ball resting in a shallow valley when a deeper valley exists nearby. The ball looks stable, but one day, a quantum fluctuation could nudge it over the edge. Some calculations suggest that our universe might be in such a false vacuum state. The field associated with the Higgs particle, which gives mass to fundamental particles, appears to lie in a delicate region where the current vacuum may not be the deepest possible state. If a lower energy configuration exists, then in principle, the universe could transition to it through a process called quantum tunneling. This is not a gradual change. It is a sudden, catastrophic event. If vacuum decay occurs, a tiny region of space somewhere in the universe would spontaneously shift to the true vacuum state. That region would have lower energy and different physical properties than the false vacuum around it. A bubble of true vacuum would form and begin to expand. Because the true vacuum is more stable, the bubble would grow at nearly the speed of light, consuming the false vacuum as it spreads. There would be no warning, because nothing can travel faster than light to tell you it is coming. Inside that expanding bubble, the laws of physics themselves would be rewritten. The strengths of forces could change. The masses of particles could change. Atoms as we know them might not be able to exist. In fact, complex structures of any kind might be impossible. Every atom in your body, every star, every planet, every black hole would be disintegrated into whatever new particles and fields the true vacuum allows. From the perspective of anything living in the false vacuum, the end would be instantaneous. One moment the universe is as it has always been. The next moment it is replaced by something entirely different. This kind of ending is terrifying because it is both absolute and unpredictable. It does not care about timescales like billions or trillions of years. Quantum tunneling is a probabilistic process. The vacuum could remain metastable for far longer than the current age of the universe, or the transition could happen much sooner. The best current estimates suggest that if our vacuum is metastable, its expected lifetime is enormous compared to the age of the universe, but not infinite. In principle, it could happen in the very far future, or, at least in theory, tomorrow. Yet there is a strange comfort hidden inside this nightmare scenario. If vacuum decay occurs, no one will see it coming. No suffering follows it, no slow decline, no struggle against the inevitable. The wave of true vacuum outruns any possible signal. There is no way to prepare, no way to resist, and no time to fear. From the point of view of any observer, reality would simply end. Vacuum decay reminds us that the universe is not just a collection of stars and galaxies drifting in space. It is also a specific arrangement of underlying laws and fields, and that arrangement may not be permanent. The endings we saw in the Big Freeze and Heat Death rely on those laws staying as they are. Vacuum decay asks a deeper question. What if the rules themselves are temporary? And if that is possible, then the next scenarios become even more unsettling, because they imagine a universe where dark energy does not just stay constant, but grows wild enough to tear space apart. Up to now, the universe's endings have felt distant and slow. The Big Freeze and Heat Death drain the cosmos of energy over unimaginable stretches of time. Vacuum decay threatens a sudden reset of the laws of physics. But there is another possibility, born from the same dark energy that quietly drives today's expansion. In this version of the future, the universe does not simply fade or flip. It is pulled apart, piece by piece, in an event known as the Big Rip. The Big Rip begins with a simple but extreme idea. What if dark energy is not just constant or slowly changing, but actually grows stronger as the universe expands? Physicists call this phantom dark energy. Instead of gently accelerating the expansion, phantom dark energy acts like a runaway engine. The more space expands, the more dark energy fills it, and the faster it forces space to expand again. The result is an acceleration that does not merely continue, it explodes. At first, this accelerated expansion would look similar to what we see today. Galaxies drift farther apart, and more of the universe slips beyond our cosmic horizon. But as phantom dark energy strengthens, its repulsive effect grows. There comes a time when it is no longer just separating galaxies from one another. It starts to overcome the gravity that holds each galaxy together. In the far future of this scenario, entire galaxies are literally pulled apart. Stars that once orbited calmly around galactic centers are thrown loose into an ever-stretching void. The process does not stop there. As dark energy intensifies, it continues to attack smaller and smaller scales. After galaxies are torn apart, gravity can no longer hold star systems together. The bonds that keep planets orbiting their stars fail. Worlds are set adrift, then destroyed as the tidal forces of the expanding universe overwhelm their structures. Even the orbit of a moon around a planet becomes impossible to maintain. Still, the expansion accelerates. Eventually, the forces associated with dark energy become so extreme that they challenge the very cohesion of matter. The electromagnetic forces that bind atoms and molecules are no longer strong enough to resist the stretching of space. Atoms themselves are ripped apart. Nuclei are torn into their component particles. The familiar building blocks of matter disintegrate under the strain of the cosmic expansion. As the Big Rip approaches its final moments, the rate of expansion of space grows so large that it exceeds any limit that could keep structures intact. Space between points grows faster than light can travel across it. Event horizons shrink rapidly. Regions of space that once could exchange signals become isolated, then shredded. Time itself, as measured by change and causality, begins to lose its usual meaning. Mathematically, this violent ending corresponds to a future singularity. The universe does not merely become empty or cold, it is driven into a state where the known laws of physics cannot even be applied. In a sense, the universe dies screaming, torn apart at every level from the largest galaxy cluster to the smallest particle. After the slow fading of the Big Freeze, the stillness of heat death, the sudden shock of vacuum decay, and the violence of the Big Rip, there is one more path the universe might take. Instead of drifting forever outward, space itself could one day turn around. The universe that began in expansion could end in collapse, in a final act called the Big Crunch. And hidden inside that collapse, some theories suggest, there might even be the seed of a new beginning. This possibility depends on a delicate competition between gravity and dark energy. If dark energy weakens over time, or if it is only a temporary phase rather than a permanent feature of the cosmos, its repulsive effect could fade. If enough matter and energy are present, gravity could slowly regain control. Expansion would first slow, then halt, and finally reverse. The vast cosmic web of galaxies would no longer be carried apart. Instead, every structure would begin to drift back inward, pulled by the combined gravity of everything in existence. At first, this reversal might be almost unnoticeable on local scales. Galaxies would still orbit, stars would still shine, and planets would still move along their paths. But on the largest scales, the distances between galaxy clusters would begin to shrink. Over billions of years, the universe would grow denser and hotter as everything falls back together. Regions that are now separated by hundreds of millions of light years would draw closer. Collisions between galaxies, once rare, would become common and then inevitable. As the contraction continues, the background temperature of space would rise. The relic radiation from the Big Bang, now observed as the cold cosmic microwave background, would grow warmer. The sky would no longer be dark between galaxies. The entire universe would begin to glow again, not from new creation, but from the compression of old light. The large-scale structure that took billions of years to form would be crushed, step by step, into a smaller and smaller volume. Eventually, if this process continues, no region of the universe can escape the pull. Galaxy clusters merge into enormous structures. Stars are torn from their orbits and thrown into chaotic interactions. Dense clouds of matter collapse into gigantic black holes. The average density of the universe climbs toward the extreme values it had near the beginning. Temperatures rise so high that atoms are stripped apart, their nuclei, until only fundamental particles and radiation remain in a seething, compressed state. In a pure Big Crunch scenario, this collapse ends in a singularity, a point where densities and temperatures become so high that the known laws of physics break down. The story looks like the Big Bang played in reverse. However, some models of quantum gravity and cosmology suggest a different twist. Instead of a final, inescapable singularity, the universe might undergo a rebound. The crushing collapse could reach a smallest possible size and then bounce, triggering a new expansion. This is the idea of the Big Bounce. In a Big Bounce picture, our Big Bang may not have been the absolute beginning of everything. It could have been the latest chapter in a much longer, perhaps eternal, cycle of universes. Each cycle would involve expansion, slowdown, collapse, and rebirth. The laws of physics might carry over from one cycle to the next, or they might change slightly each time, creating new cosmic histories. Time itself might be cyclical on the grandest scales, with no true first or final moment. This vision is deeply speculative, but it is grounded in a simple and profound question. If the universe had a beginning in the Big Bang, what set the initial conditions? A previous universe collapsing into a Big Crunch and rebounding into a Big Bounce is one possible answer. Whether or not this is correct, it pushes us to think beyond a single lifetime of the cosmos, and it prepares the stage for an even stranger idea where our universe may be just one of many, each with its own laws, shaped by dark energy in ways that determine whether life like ours can ever exist. By now, dark energy has shaped every possible ending of our story. It decides whether the universe freezes, rips, collapses, or quietly fades. But there is an even deeper question hiding underneath all of this. Why does dark energy have the strange, tiny value it does in our universe at all? If dark energy were much stronger, the universe would have expanded so quickly that gravity could never have pulled matter together to form stars and galaxies. Structures would have been torn apart before they began. If dark energy were much weaker or negative, gravity might have overwhelmed expansion early, causing the universe to recollapse long before complex structures or life could appear. Our universe seems to sit in a narrow window where dark energy is small enough to allow galaxies and stars to form, yet large enough to dominate the cosmos today. This suspicious balance leads to a provocative idea called the anthropic principle. It does not say that the universe was made for us. It says that we can only find ourselves in a universe where conditions allow observers to exist. If there are many possible universes, each with different values of dark energy and other physical constants, most of them would be sterile, empty, or short-lived. Only a tiny fraction would allow stars, planets, chemistry, and eventually life. Naturally, any intelligent beings that arise will look around and see a universe that appears finely tuned for their existence. To make this more than philosophy, some theories in modern physics suggest that a multitude of universes could actually be real. In certain versions of cosmic inflation, the rapid expansion that may have taken place shortly after the Big Bang does not happen just once. Instead, inflation continues in other regions, constantly spawning new bubble-like universes, each with its own properties. In this picture, our observable universe is just one bubble in a much larger multiverse, with dark energy taking different values in different bubbles. In string theory and related ideas, the space of possible configurations of fields and dimensions is vast, perhaps unimaginably so. Each configuration could correspond to a different universe with its own laws of physics, particle types, and dark energy density. Most would be inhospitable. A few would have the delicate balance needed for long-lived stars and complex chemistry. We live in one of those rare pockets where dark energy is small enough, and the conditions are right for life to emerge and ask questions. This multiverse view offers a potential explanation for the fine-tuning of dark energy. Instead of searching for a single deep law that forces dark energy to have exactly the value we measure, it suggests that all possible values exist somewhere. We simply inhabit a region where the value allows our existence. It is a selection effect. We do not see the universes where dark energy is too large or too small, because no observers ever form there to see them. However, there is a serious problem. There is currently no direct observational evidence for other universes beyond our own. The multiverse remains a speculative extension of our theories, not a confirmed feature of reality. It may be mathematically consistent and even natural in some models, but without measurable signatures it sits in a strange place between physics and metaphysics. Some scientists embrace it as a way to understand dark energy and cosmic fine-tuning. Others resist it, preferring explanations that rely on testable mechanisms within a single universe. The universe is not a static stage, it is a changing story, and we are living in a brief, special chapter of it. The earlier parts of this journey showed how dark energy can lead to a big freeze, heat death, vacuum decay, big rip, big crunch, or even a big bounce, and how multiverses and exotic stars might exist in deeper theoretical pictures. All of these possibilities point to one idea. We live in a temporary cosmic era where stars shine, galaxies exist, and complex life can form. In the distant past, the universe was too hot and simple for life. In most possible futures, it is too cold, too empty, too torn apart, or too radically transformed for life to survive. That makes the present moment incredibly rare. Dark energy, which will one day help decide the universe's fate, is also part of the delicate conditions that allowed galaxies and life to form at all. Science does not yet know which ending is true, or whether our universe is unique, but one fact stands out. For a brief time, the universe became aware of itself through us, and chose to ask how it will end. That awareness may be temporary, but it gives our existence profound meaning.